it's kind of, bless you, it's kind of a lost art when you think about just long division in general, in terms of numbers wise, because honestly, you guys never really did a lot of it. You did some multiplication stuff. I look at long division nowadays as I try to set up as fractions, but I'm going to show you to remind you of what long division looked like numerically the old-fashioned way. Because what we do here with long division with polynomials is that eventually it'll help us find what are called slant asymptotes. Remember that? Yeah, I do. So, long division wise, if I want to figure out, I don't know, 13 into now I'm just making up really, really, really funny numbers. Now, do you remember the rules for doing so? Yes. All right. What would you be trying to do first? Yeah. Does 13 go into 2? No. Does 13 go into 27? Yes. How many times? Twice. So where would you place the 2? Over the 7. Okay. So 2 times 13 is. Now what do? Subtract. Okay. Drop the 1. Does that work? No, so what do I put up top? A 0, good. I get another 0, subtract it out. Bring down the 4. Okay, now we're going to have to math. Now we know 13 times 10 would be 130. Subtract 13 from that, you get 117, so that'd be 9. So this has to be an 8. Thanks! $13 times 8, then, let's see, be end in a 4. 104, okay? Subtract that out, we get a 10. Bring down the 3. I know, right? So now we know it's going to be a 7. Was it 91? And then what was our last one? A 6? Actually, this works out kind of nice because all the numbers are right around the same area. So that would be back to an 8, right? Because it was 114. If it was 9, no, 9 would end in a 7. Oh yeah, it was 9. Sorry. Yeah, you'll get over it. So 130, so that would be, what, 117 we said? Okay. And then we finally subtract out, we're left with a 9. What is that 9? It's a remainder, okay? Now, you did this a couple of different ways. You could continue on and get your decimal and go on your merry way, but remember, the 9 represented 9/13ths. Remember that? Or not R9, yes, remainder 9. I see what you're saying, but that's what that represents, okay? So the couple of things that I want to show you then is that if I do this with a polynomial, absolutely nothing changes. The only thing that changes is that you'll have a variable, and you'll have to look at some exponent rules. Everything else that you just did about what times what to multiply it in, to subtract out, and go back and forth, all of that doesn't change. Except, right?
Absolutely nothing.
What's that? See ya. Good to see you. So, put away the laptop. Thanks. So, what happens here, we talk about polynomial stuff. There's a few rules that you have to follow. One of which is that you have to be in descending order, and you have to have placeholders for any missing parts. Placeholders have to be wherever anything's missing, whether it's like an x squared, an x, a constant. You have to have a placeholder for any piece. By now, we all understand that if we have a third-degree polynomial, we're going to have 4 parts to it, correct? We're okay with that? So do we have all 4 parts? Yeah. Is it in descending order? Yes. So here's what happens. Just like we did with the division of how many times did 13 go into 2, it didn't work. But 13 went into 27. Well, we do kind of the same idea. What do you multiply 2x by to turn it into a 2x cubed? X squared, good. Now, if I'm looking at x squared, just take a guess where you're going to put that over. The x squared. That's what I'm getting at. Whatever you're multiplying it by to start with, you line it up with whatever that piece is. And then you just distribute that to what's out front here, just like you did with long division. We did 2 times 13, and we wrote down 26. Here it's going to be x squared times the quantity 2x plus 3, and I get 2x cubed plus 3x squared. It's a thing, yes. It's eerily similar to what we did when we had long division, where we had that 13, 27, we put a 2 here, 2 times 13 was 26. We just multiplied 2 with the outside, and we rewrote it underneath. The only difference here is that there's some variables thrown in. Okay? We threw a couple of variables at you. What did I do between the 27 and the 26 when we did long division? You subtract. What do you think I have to do here? Same thing. You still subtract. So what happens then is that we do a subtraction twice. Remember we did adding and subtracting polynomials before? We just write them out like that? Now, I know the first one goes away, but then what's negative 7 minus 3? Negative 10. Good, yeah, negative 10x squared. Negative 10x squared, and then I bring down the negative 17x. Again, what I want to do now is, what do I multiply the 2x by to turn it into a negative 10x squared? Negative 5x. What I'm trying to get you guys to see here is that you're trying to eliminate this first term. Every time you're doing it, you want to turn whatever that first term is. You want to figure out what do you multiply this guy by to turn it into this. That's what we're doing for each and every piece. Yes, ma'am. You always will be able to, because you could always use a fraction. But to start, they're going to be they should be pretty straightforward. Okay. All right. So I distribute out that negative 5x. I get negative 10x squared minus 15x. Very good. And I subtract them. What's negative 10 minus negative 10? Wait. So, all right, let me rephrase this here, because everybody's saying weird stuff. Negative 10 minus negative 10 is 0. Negative 17 minus a negative 15, negative 2. And I bring down the negative 3. Then, but wait, there's more. Then I have to figure out what do I multiply 2x by to turn it into negative 2x. Negative 1. So I multiply out by a negative 1, distribute that. Is there a remainder? No. So what we did here, is that we divided out a 2x plus 3. When you divide something out of a term, aren't you factoring it? Especially if you have no remainder. Okay. Now, it looks weird, but in the grand scheme, is it difficult? No, and just like I was saying, like, you know, there will be times that, yeah, you might have to multiply by a fraction, but it's going to be like if there's a 5 and a 2, how do you multiply, what do you make a 2 by to turn into a 5? Then it would be, you know, 5 over 2, things like that. So it's not going to be awful. But what this is going to allow us to do is, as we go further along throughout the rest of this polynomials, because the last bit of polynomials really is, how do you take really crummy looking stuff, factor it? And that's where we start with this long division, and we start to get into synthetic division. Then we're able to talk about how do you place zeros, how do you work backwards, how do you do your dances, why does everything happen the way it does? It's because algebras. And this is, yeah, it does all this crazy stuff in this chapter, because when we get to what are called rational expressions, we start graphing these things, you're going to have, at some point in time, what are called slant asymptotes. We all know that asymptotes are what happen when you can't divide by 0. You have these vertical asymptotes, correct? Well, what happens sometimes, depending upon polynomials, when you graph them, they could have what's called a slant asymptote. And basically, you guys had something like that when we dealt with conics. Okay? When we did that with conics, it was a little bit different. When we get to rational expressions, we're going to do polynomial division to find that out. And it's a really easy thing as we get there. Right? So, you can also do that with even higher degree things. Very good. You saw that right away. So we have 2x to the 4th plus 3x squared plus 5x minus 1. Where do I need a placeholder? I need to put a 0x cubed in here. I'm sorry, 0x squared. Thank you. And you go through the whole process again, and it does not matter that you're dividing by a trinomial. The process by which we do this is exactly the same. Again, you're going to ask yourself, what do you multiply an x squared by to turn it into a 2x to the 4th? 2x squared. What do you, repeating the question, what do you multiply x squared by and turn it into a 2x to the 4th? So that means I'm going to multiply it by a 2x squared. Take a wild and crazy guess where you're going to place that in yeah, over the 0x squared part. Distribute that in. We get 2x to the 4th minus 4x cubed plus 4x squared. I would make a suggestion. When you're writing out the division, make it a little bit wider. And you use a little more space going left to right when you need. It just helps keep it clean as you're writing all this stuff in. And then what do you think we do? Or what do you suppose we should do? Subtract everything. Good. So you have 3 subtraction problems. 2 minus 2, gone. 3 minus negative 4, 7x cubed. 0 minus 4, and bring down the 5. Yes, it's a squared. Thank you. All we did was just subtract and rewrote. Next question, what do you multiply x squared by to turn it into 7x cubed? Once again, 3 subtraction problems. Seven goes away. Negative 4 minus negative 14. 10. And then it's 10x squared. Oops. And then we'd be what? Minus 9x? And bring down the 1. which means, what do you multiply it by now? 10, good. So I multiply everything by a 10. We get 10x squared minus 20x plus 20. And what do we get? 11x minus 21. Now, that, you'll notice, is a degree less than what we were dividing by. When you get to a degree less that you're dividing by, and it's not, obviously if it's not 0, that then becomes your remainder. So how we write our remainders with long division with polynomials is a little bit different than, you guys wrote R. We're not going to write R 11x minus 21.
Why R?
Little parents are R. Yeah, yes, with the hook. You got to have the hook because that's a prop. Yeah. R. R. Should I walk around like with one leg? And it gets scurvy?
They had scurvy.
And that's how you write remainders. When you write your remainders, what you want to remember that you do is whatever the sign of the remainder is, in this case it was positive, I would write plus 11x minus 21 over. And like I always say, there's a reason why we do it this way, because later on, when we do this polynomial division, the remainder is the equation of the slant asymptote. Of course it is, exactly. So there's a little foreshadow here that, like in a month or so when I talk about this again, you guys all can't look at me like I'm really crazy, just sort of crazy. I say, hey, you've seen this before. And then I'll go, arr, and then you go, oh yeah, I remember that. So let's talk about one other quick thing here. There's a thing called synthetic division. We did. A week ago, we did what was called synthetic substitution. When we did synthetic substitution, you were literally saying, hey, substitute this in, go through the process, and get an answer at the end. That was what we found it to be. When we talk about this thing called synthetic substitution, or excuse me, synthetic division, synthetic division is when you check to see, is this a term of that? Now, if x minus 2 is a term, that means it's in parentheses. What's its 0? 2. So if x minus 2 is a term, 2 is the 0. You okay with that? Thanks. We're dividing by 0 now. Sweet. So here's what we do. In order to determine whether or not the term is a term of that larger polynomial, we use synthetic division. It's the same thing as synthetic substitution, but it has a different name. So like we did before, remember this little chart like that? what did I put in that row? Do you remember? I would put these coefficients in. Okay? I put the coefficients of all those in. It's a third degree polynomial. It should have 4 parts, and it does. So I would write 1, 2, -6, and -9. Now what I'm checking to see is x minus 2 a term of that polynomial? Is it a factor? So what I do to check that is I divide by its 0. So I'm not dividing by 0, I'm dividing by the 0 of the term. Okay. Now, yeah. So if my term is x minus 2, my 0 would be 2. Okay. So I put a 2 out front. Now, remember, the process for doing these things is you always drop the first term to here. And what do I do to the outside numbers? Multiply, good. What's 2 times 1? Good pause, good job. What's 2 plus 2? 4. What's 2 times 4? Get out of my class. Add them together. 2 times 4 is 8. -6 plus 8 is 2. 2 times 2 is 4. -9 and 4 is -5. Now, what that means, since my last value is not a 0, that means that 2 isn't a 0 of the function. And if 2 isn't a 0 of the function, that means x minus 2 isn't a term of the function. So what's happening here is, by using this little trick of synthetic division, you can factor things out as you go through. And I heard you say that this takes a long time. Believe me, it was a lot. Oh, I thought you were saying this takes forever. As we get going into this stuff, this becomes one of the most efficient ways to factor. It's faster than most of the things that we show, but it takes a while to get us to this point. All right. So I know that x minus 2 is not a term. So I do the same thing and I check in with x plus 3. Well, if x plus 3 is my term, what would be my 0? -3. So I do the same thing with the -3. What's -3 times 1? -3. What's 2? What's 2 plus -3? -1. What's -3 times -1? What's -6 plus 3? What's -3 times -3? Did I end up with a 0? Now here's what happens. Since that that ends in a 0, that means that -3 is a 0, which means the term that creates a -3 is x plus 3. So if I divided it out, what I'm doing here is I'm dividing out an x plus 3. I factored out an x plus 3, which means when you factor something out, it generally goes down 1 degree. If I took out an x out of an x cubed, what's left? An x squared. Now, remember this? These were the coefficients of my polynomial to start with. Now, what happens here is that since those were the coefficients of the polynomial that I started with, I factored out a term of x plus 3. That now leaves me new coefficients. Yeah. As you factor things out, as you factor things out, you're taking a degree out of it. Oh, it's plus. I'm sorry, the marker didn't go all the way through. So there's a plus. Sorry, when I didn't know the marker had a spot there. Yes, sir. I'm going back to that. Remember how this up here was x cubed plus 2x squared minus 6x minus 9? Remember how that worked out like that? As I divide something out, if I take something out, I took out a 0 of -3. If -3 is my 0, that meant that I was able to take out the term x plus 3. So if I take out an x out of x cubed, what am I left with? X squared. What I'm doing here is it takes out that whole term. So every time that you synthetically divide something and you end up with a 0, that means that that string of digits prior to it become new coefficients of a newly generated polynomial. So what we're getting at here is that this idea of x cubed plus 2x squared minus 6x minus 9, yeah, we could have factored it via grouping and gone through some stuff and trying to figure out stuff. But this is another way. If I know that I have a 0, if I'm given a 0, I can factor it even faster, okay, and go from there. Is there anything that I can do to factor out what's -3 that adds together to get -1? The answer is no.
No.
And then you would be done. Okay? Look at Owen. Let's do this synthetically. Once you divide this by x plus 4, if I want to divide it by x plus 4, right, you always divide by the terms 0. Okay? We only divide by the terms 0. So we have x to the 4th minus 16x squared plus x plus 4. That means I have a 4th degree polynomial, which means how many terms should I have? I should have 5 terms in my strand. So my coefficients would then be 1, 0, -16, 1, and 4. I put in a placeholder in for the x cubed. What do I divide that by? What do I put on the outside? -4. Very good. Remember, always divide by the terms 0. Okay? Always divide by the terms 0. First step is to bring the 1 down. What's -4 times 1? -4. -4 plus 0. -4 times -4. -16 plus 16. -4 times 0. 0 plus 1. And then -4 times 1. Is -4 a 0 of that polynomial? Good. That means I was able to factor out the term of, yes, sir. And then it would end like in 6. And then that means it's not a term. Then you couldn't factor it out. All right. So I ended in 0, which means that -4 is a 0. If -4 is a 0, its term is x plus 4. So you're able to factor out an x plus 4. Now, it started as a 4th degree polynomial, which means what is this now? 3rd degree polynomial. So I get x cubed minus 4x squared, 0x plus 1. bad, is it? It looks like it's going to be god awful.
Yeah, it's going to be something else.
It really isn't. I'm not. What's going to surprise? Honestly, what's going to suck with this is that you're going to have to do it like 4 or 5 times before you find a 0. But as you get good at doing synthetic division, it's super fast. And even if you make a mistake and you miss a 0 to start out with one of the first easy ones, like a 1 or a -1, you'll find it with like a 2. And then you always go through it. Because when you're factoring stuff, there's many ways of going about it. And you can accidentally screw something up and miss one, but yet you can still do it. So it's not like it's not like you're going to hit a wall and go like, I can't do it anymore. Okay? All right. Let's do this. What section is this? 6.5? Yeah, I'm going to give you a couple of these. I normally don't like to do a lot of stuff on Friday, so. Scroll. Hello? Oh, there it is. The heck was that? Hello? All right. Let's do this. On page 356, yeah. On the 356, let's do, yeah. What was it, 356? Yeah, we will. All right. Let's do those. When you guys, hey guys, when you get to the synthetic division, they may or may not end in a 0. If they don't end in a 0, it's okay. Just double check, make sure you didn't screw something up. But I'm pretty sure that I don't remember off the top of my head they all do. But what I would like you to do is if they do end with a 0, rewrite the polynomial that you created, like we just did in class. How I said drop the degree. There's a reason I want you just to get accustomed to doing that, because as we go along, yes, this becomes a way to factor. So it's a really nice thing to look at. Yes, ma'am. They might be. But you don't have to worry about that for today. We'll look at more of that Monday, Tuesday. I'm just getting like foreshadowing. You know, it's like something's going to happen. Algebra's going to algebra. Oh, synthetic division is so much fun. Synthetic division is so much fun. I like synthetic division because it's so much fun. So much fun. So much fun. So much fun. Fun.